So, a random question, did anyone have trouble logging into the course website from off campus? For some reason I wasn't able to log into it from home, so I was wondering if anyone else had the same problem. Maybe it was just down in the morning. In fact, I wasn't able to log into illinois.edu either, so something was off. Give it a couple more minutes. Okay, so let's start. So I'm going to be trying to use PDFs for this class because the relational algebra symbols that I drew on the PowerPoint aren't rendering on the PowerPoint, which is bizarre. So I'm going to try and see how the PDFs look like. If not, we'll resort back to PowerPoint and I will draw the symbols as they appear. Okay, so let's see how this goes. The only downside with the PDF that I've identified so far is that I have to press the keyboard as opposed to the mouse, and all of the notations disappear. So they stay across slides. So I will have to erase all of them every time I move to a new slide. So we'll see how that goes. It's painful, but maybe at least we'll get to see the symbols. Okay, so we were talking about these basic relational algebra operators, and then we moved on to the advanced relational algebra operators in the last class. So the basic ones were the set operations like union and difference. The constraint for the union was depicted with a U. The constraint for union was that the relations must have the same schema. The difference, once again, the constraint is that the relations must have the same schema, and the output is what is in relation 1, but not in relation 2. And then there was a selection condition, which is represented using sigma with a subscript condition. So for instance, if I wanted to find all the employees whose salary is greater than 40,000, I would depict it using something like this, right? So this allows me to select all of the tuples in employee with salary greater than 40,000. Okay. All right. So the selection example, basically what the selection operation does is it eliminates all of the tuples that are not relevant. So in this case, I have a query where I want to find the employees with salary greater than 30,000 and department ID is equal to 2. So it will eliminate tuple number 1, tuple number 2, and only leave tuple number 3. So the Alice tuple. Okay. Then there was a projection operation which was depicted using pi. That was a notation for it. The projection operation, instead of eliminating rows, it eliminates columns. One thing to note is that since we are always dealing with a set of tuples, we are going to be eliminating the tuples after we've gone and deleted those columns. Okay, so the notation for the projection operation was pi with subscript corresponding to all of the attributes that you have you want to retain in your final output. So the set of attributes A1 through AN must be a subset of the entire set of attributes that are present in R, because you can't select an attribute that you don't have, right? So the output schema is going to be A1 through AN. For example, if you have a relation employee with 4 attributes, SSN, name, department, and salary, you can just do pi of SSN and name, which allows you to select just those two columns and eliminate the remaining columns. Implicitly, what that's going to do is it's going to collapse the tuples down such that you eliminate the duplicate tuples. Okay? So as an example of that, if I had this relation corresponding to SSN name, department ID, and salary, and I did a projection operation with SSN and name, then I would get basically just these two columns, and since all of the tuples in these two columns are distinct, I don't need to eliminate any tuples, so that's good. If I wanted to select the department ID, all I would get is this column, in which case I would have to eliminate one of these two copies of 1, so it would be dep ID and 1 and 2. Okay, so that would be my resulting relation. Okay, so then there's a Cartesian product which allows you to combine information across tables, denoted using this X symbol. And one special case is if the attributes in both of the relations have the same name. If they have the same name, the convention that we are going to use is that we're going to rename them as R1.A and R2.A, such that we can distinguish them. Otherwise, the output schema is basically the union of both of the schema. So it's a listing of A1 through AN followed by B1 through BM. So how does an example of this look like? Well, if I had these two relations corresponding to the employee and dependents, the employee cross product dependence or Cartesian product dependence would basically combine every tuple in employee with every tuple in dependence. Okay, and the attributes would be basically the attributes in employee and the attributes in dependence. So this we saw already, right? And then you have the renaming operator again. This is maybe part of the extended algebra, not the basic operations, this is the extended operations. This doesn't change the relational instance, it doesn't change the data, it only changes the schema, it changes the metadata in some sense associated with the data. So if you have a relation corresponding to R with attributes A1 through AN, and you want to transform that to name S, attributes B1 through BN, you can use this row notation to do that. So here I'm renaming employee with name and SSN into row of renamed employee, which is the name, new name for employee, and last name and social security number. Okay, so that's that. This is an example of the previous sort of relational algebra operation. Now let's move on to the derived relational algebra operations. Any questions about this so far? Yeah.
What was the main difference between the Cartesian product and the union?
So the Cartesian product is basically combining information across two relations. These relations don't necessarily have to be the same schema. They are basically you are matching information in one with information in the other. Union is basically taking the information in two relations, unioning them. So basically collapsing the set of tuples. So that's a way to think about that. Okay. All right. So derived relational algebra operations, simple one is intersection, which is derived using the difference operator. Once again, the relations must have the same schema to be able to apply the intersection operator. This is again a straightforward set-oriented operation, because remember, once again, relations are sets of tuples, so you should be able to treat them just like sets. Okay, now let's get to the joins part. So the joins part are slightly more interesting. So a theta join is one special type of a join. So a theta join is basically a Cartesian product followed by a selection condition. The notation for a theta join is R1 with this bow tie symbol with a subscript theta R2, where theta is a condition. So if the input schemas are A1 through AN and B1 through BM, then once again, like the Cartesian product case, the output schema is a concatenation of these two lists. So it is A1 through AN and B1 through BM. And the way to think about this theta join operator is, once again, it's depicted using this bow tie symbol with the theta subscript. This is equal to or equivalent to a sigma of with subscript theta of R1 cross product with R2. Okay, so think of it as you're taking R1 and R2, doing the cross product, and then applying a condition on the result. So this is a derived operator. It's derived using sigma and using the cross product. So just like the Cartesian product or the cross product case, if an attribute in R1 has the same name as the attribute in R2, then we are going to need renaming. We are going to the simplest case would be you just sort of have them as R1.A and R2.A. If you want them to be renamed in some other way, you can use the row operator. Okay, but by default, this would get renamed as R1.A, R2.A if there are two attributes which have the same name in these two relations. Any questions? Okay. All right. So this is an example of the theta join operator. So here I'm trying to do a theta join of these two relations, cells which contains bar, beer, and price, and bars which contains name and address. And maybe I want to find or match the tuples across these two relations where cells.bar is equal to bars.name. So this attribute is equal to this attribute. Okay, so here I'm saying cells, once again a bow tie with cells.bar is equal to bars.name. Here I'm being overly specific. Given that bar and name are distinct attributes, I don't necessarily need to say that. I can just simply say bar is equal to name. That's totally fine. But here I'm being overly specific. That's totally fine, because again, this is a theoretical language. As long as we are being clear about what we are expressing, that's okay. Okay, this is not a formal. This is not a formal query language. This is a theoretical language. So as long as we are being clear about what we are expressing, this is okay. In this case, I'm saying cells.bar is equal to bar not name. That is perfectly fine. That's absolutely clear. That's great. So that's how I'm expressing this query. I'm basically saying make sure that these two attributes are the same. And the result is going to be a concatenation of the attributes of cells and the attributes of bars. So that's bar, beer, and price, and name and address. And basically all tuples corresponding to matches across these two relations are added, except for those where the bar is cells.bar is not equal to bars.name. And there are basically 4 of those that get eliminated, so you only have 4 tuples left. And if you want to be clear about which ones they are, so basically you can match up the Joe's ones and they get attached to this guy, the Sue's ones, they get attached to this one, and so you have 4 tuples as part of the output. Okay? All good? All right. So that's a theta join. An even more special case is the natural join. The natural join is actually something that occurs extremely often. The natural join is denoted even more simply than the theta join with just the bow tie. And implicitly what it's trying to do is to try to associate data in these two relations while ensuring that the common data is associated with each other. Okay, what do I mean by that? So let's say I have relation R1 with attributes A1 through AN, relation R2 with attributes B1 through BN. The output schema is basically a union of the attributes in these two relations, as opposed to simply listing both of those attributes next to each other, right? So here it's a union of those attributes. It's not simply A1 through AN followed by B1 through BM. Okay, so in the previous case, if there were attributes that were had the same name, we had to do a renaming. In this case, we don't have to do a renaming. We just collapse the schema down and do a union of the attributes. And the condition is that I want to combine all of the pairs of tuples in R1 and R2 that agree on the attributes that are in common. Okay? So let me give you an example. So let's say I have R with A comma B and S with B comma C, and I do R natural join with S. What it's going to do is it's going to associate tuples in R and S that have the same value for B. Okay? The output schema for this guy is going to be, let's say this is Q is equal to R dot S. Q is going to have an output schema of A, B, C. Okay? If it was a theta join, Q would be A, R1 dot B, or R dot B, S dot B, C. Right? This is a special case of a theta join, or a slightly different variant of a theta join, where these two attributes are collapsed into one, and you're associating the tuples in these two relations that have the same values for the common attributes. Okay? So another way of thinking about this is it is roughly equivalent to a cross product followed by a selection, but you're also eliminating the attributes that are in common. Okay, so let me give you some examples so that this becomes a little more clear. I'm going to erase this. Okay, so if I had these two relations, employee and dependents, and I did a natural join of employee and dependents, it's going to associate, so notice that the employee and dependents have this attribute SSN in common. So it's going to associate this tuple, the John tuple, with the Emily tuple, and the Tony tuple with the Joe tuple, because they have this value in common, right? So the SSN value in common. Okay? So the output is going to be this tuple, John with 99999, is joins with this tuple corresponding to Emily, and this tuple corresponding to Tony is going to join with this tuple corresponding to Joe. So your output is going to look like this. Okay, so basically you're correlating the information in these two relations, eliminating the common attributes, making sure that the common attributes match, and eliminating, smushing all of them together to give one output relation. Yes?
I got it.
You got it, okay. So essentially you're, yeah?
Do you consider that every one of the common attribute tuples has the exact same value?
Yeah, so let me clarify and then see if your question gets answered. So let's say you have multiple common attributes. So you have so R contains A, B1, B2, B3, and S contains B1, B2, B3, C. The resulting relation is going to have schema A, B1, B2, B3, C, and the tuples in this and this, so let's say you have a tuple R and a tuple S, small r and small s. These two are going to get joined if R dot B1 is equal to S dot B1, R dot B2 is equal to S dot B2, and R dot B3 is equal to S dot B3. So all of those attributes that are in common need to match in order for them to get joined with each other and result in a tuple Q in the relation capital Q. Does that answer your question?
So if they don't have the same value, then they just get dropped?
Yeah, you would just drop them. So another way of thinking about it is you consider all combinations of tuples in capital R and capital S. If they don't satisfy this condition, then they don't become part of the output. If they satisfy this condition, you would join them and give them to the output. So as an illustration of that, here you had John and Tony in this relation and Emily and Joe in this relation. You could have had 4 tuples in the output because you had 2 tuples here and 2 tuples here. Out of these 4, 2 of them were eliminated, so you only got 2 as a result. Okay? Those which matched on the SSN attribute. Yep.
If we tried to do a natural join with name and dname, would we get an empty table or would we get all 4?
Good question. So the question is, if you did a natural join, let's say you had a relation R containing, actually we'll get to an example of this, but a relation R containing A and relation S containing B, and you did a natural join of these 2 guys, so R natural join with S, what would you get? Any guesses? Empty? No. So the answer is RAB. Basically, the way to think about this is there are no attributes in common, right? Because there are no attributes in common, every tuple in R associates with every tuple in S, and therefore you're going to basically get the cross product. Okay, so you're going to get Q. So if you follow the same rule here, right? The rule here was that the output relation is going to be all the tuples that are in R but not in S, all of the tuples in S but not in R, and all of the tuples in all of the attributes in R but not in S, all of the attributes in S but not in R, and all of the attributes in common. So that is what Q contains. In this case, Q is all of the attributes in R but not in S, that's A, all of the attributes in that are in common, that's nothing, and all of the attributes in S but not in R, that's B. So Q is going to be A comma B. So that's going to be the schema of Q. And essentially within Q you're going to associate all of the tuples in R and S that have the same values for the common attributes. The common attributes here is an empty set. Because it's an empty set, by default all of the tuples match. Because all the tuples match, you're going to essentially get a cross product. Is that clear? Okay. All right. So that's an example of the natural join. Let's keep going. I wanted to clarify one more thing. So the question is, how do we express a natural join as a combination of the basic relational algebra operators? And this is actually not completely straightforward, and that's what is written here. So let's try to unpack this. Okay, so the way to read this is you start by looking at the dependence table. So here I'm doing a join, natural join between employee and dependents. I would start by looking at the dependence table. I would rename it such that dependence now has SSN2 and dname, for instance. And then I actually, okay, so I don't necessarily need to do this. This is just one of many ways to do this. But let's say I decide to rename dependence such that it has an attribute SSN2 and dname. Then I decided to do a cross product between employee and dependents. Once I do a cross product between employee and dependents, I have a relation which is name, SSN, SSN2, and dname, right? And it contains all 4 tuples corresponding to every tuple in employee and every tuple in dependents. Then the sigma corresponding to SSN is equal to SSN2 is going to eliminate all but 2 of the tuples. Okay? So only 2 tuples will be left. And the final operation is a projection operation. I'm going to throw away all of the attributes that I don't want. Does it make sense? So another way of thinking about the natural join is essentially you're doing a cross product and then you're doing a selection followed by a projection. The rename operation in this case, we decided to do it right away at the start. You can do a rename operation later on also if you choose to. Does this make sense to you? There are other ways of expressing this. Any guesses on what might be another way of expressing a natural join as a combination of regular basic relational algebra operations. Any guesses? Or how would you do that?
It's just sort of like an overlap of, well, if you have two of the same elements, then you are just going to sort of overlap them.
Yeah. But the thing with the OR operation or the union operation, which is probably what you're referring to, is that the schemas need to be the same. If the schemas are not the same, you can't necessarily apply the union operation. Any other guesses? Okay, let me give you a hint. So the hint is the first operation, if you look at this nested expression, the first operation that we did was a rename operation. What if we didn't do a rename operation as a first step? What if we did a cross product as a first step? Okay, so let's start with that, and then let's see what problems that leads to. Okay, so and I'm doing this on the fly with you, so we'll see how that goes. So the first thing that I'm going to do is I'm going to take dependence and I'm going to do a cross product of that with employee. Okay? So that's my first step, let's say. Now what is my my resulting relation going to look like? Yep.
You have two SSNs, one name and one rename.
Yeah, so you'll have, but the SSNs, in order to identify the SSNs, you will have them prefaced by the relation name, right? So it would be the schema of this relation would be name, employee, I'm just writing EMP for short, I do mean employee, dot SSN, dependent dot SSN, and dname, right? So this is a schema of the resulting relation. Okay, so what could I do next? There are again many options for me. What might I be able to do next? Yep.
You can select the one that where like employee SSN equals dependent.
Right. So she said you could use, for instance, a selection operation, so a sigma operation where employee SN equals dependent SN, and that's perfectly valid. Okay. So right? Okay, so that's good. That eliminates two of the tuples that we don't want, right? What next? Yep. Again, we have two options. Okay, so here one thing to notice is that we had two options. We could have done a rename instead of the sigma. I'll let you go think about that. But here we chose to do a sigma, which is the selection. Okay, what next? We're getting the same thing essentially. Yeah.
So technically, if it were the other way around, it would technically have been projection first and then selection.
Right. So again, we have multiple options. We could do a row to rename stuff, or we could do a projection. I'm just going to do a projection for fun. Okay, so let's do projection. So we have 4 attributes here, right? And I know that those 4 attributes and the tuples in that relation are already being matched for employee and dependent SSNs being equal, right? Now that I know that they are matched, I can go ahead and eliminate one of them because I don't really need them, right? I don't need both of these attributes. So I'm just going to go ahead and say my renamed, or rather my projected relation needs to contain name, emp.ssn, and dname, right? So I've shrunk this relation down, I've eliminated a column. I now have the 3 columns that I need, okay? Unfortunately, the 3 columns that I need, for one of those columns or one of those attributes, the name is not correct. I want it to be SSN, not emp.ssn. So I'm going to do a row with um, I can change the relation name if I want, but maybe I will. Let's call it new or something, new emp. And within the parentheses, I have name, SSN, and dname. Right? So essentially what I'm getting is the three attributes that I wanted, and I have renamed this emp.ssn to give SSN. Yes?
For this question, you can't really switch projection and selection, right? Because like, or else you can't really select where SSN is the same.
Correct. So in this case, you can't really swap the selection and the projection operation because you need to perform, if you're thinking about this bottom up, you need to be able to figure out which tuples match first before you throw away the information that you don't want. So if you throw away the information prematurely, you won't be able to figure out what matches. Make sense? Any questions about this? Okay. All right. So I'm going to keep going. Let me erase this guy. Okay, so this was an example of a natural join with attributes A and B in R and B and C in S. Once again, you're associating all the tuples in B or all the tuples in the two relations which share the same value for B. In this case, you could have 4 times 3 tuples, which are 12 tuples, of which you only get 5 in this case. Okay. All right. So, to some quick questions. This shouldn't be hard, given that we already had a question about this. So, given schemas are A, B, C, D, and S, A, C, E. What's a schema of R join S? So, it's going to be just A, B, C, D, E, right? Essentially, you take the two guys and then take their union. That's going to be the schema of R join, natural join with S. Given R is ABC and S is DE, what is the schema of R join S? This is a question that was already asked. In this case, it would be A, B, C, D, E once again. And we have a concise description of what R natural join S would be. In this case, R natural join S is nothing but R cross product with S. Okay? Okay, so another sort of special case. Let's say you have R with AB and S also with AB. What do you think R natural join with S is? Sorry, I can't hear you. Yeah? That's a schema. What can you give me a succinct description of? So you're right, the schema is A comma B. What's a description of what R natural join S will be? Yep.
It equals R and it equals S.
It equals R and it equals S. What does that mean?
Like R natural join S equals R equals S, right?
It's actually the intersection. So R might not be equal to S, right? So if R is not equal to S, then there's no, you still want R natural join S to have a single value. So R natural join S is going to basically associate the tuples in R and S that share the same values for the common attributes. What that means is you're going to essentially do an intersection because the tuples in the two relations that are going to match have the same values in the attributes that R and S contain. So if there is no tuples, if for every tuple in R there isn't a tuple in S that matches, you won't be able to get that as part of your output. So essentially what you're doing is an intersection operation. Okay? Cool. So let's get rid of this. Okay, so this is another special case of theta joins or a generalization of natural joins, but this behaves more like theta joins and natural joins. Is this type of join which is called equijoin. Here, essentially, this is a theta join with the restriction that the theta is an equality predicate. Okay, so it's not very interesting special case from the purpose of syntax, but actually from the purpose of implementation in practice, equijoins are actually really important, and there's a lot of research in trying to do it efficiently. Okay, so this was a summary of the joins and cross products. We talked about the cross product, we talked about the theta join. Another special case of the theta join is the equijoin, which is an equality predicate, and then the natural join, which is trying to eliminate the common attributes and correlate tuples in the two relations that share the same values for the common attributes. Okay, so that's a summary of relational algebra, the constructs at least. Now we're going to be telling you about how you can actually use these constructs in queries. Okay, so this is something we've already covered, so maybe I will skip this. So this is just expressing a natural join using the basic operators. And on this slide I say there are at least 3 solutions. I think that's true. There are probably even more than 3. Okay. So relational algebra has 6 basic operators and many combined or derived operators. In order to assemble expressions or queries, you can combine them in various ways. These are called relational algebra expressions, or colloquially called as relational algebra queries. There are many ways in which you can construct these queries. You have 3 primary ways. One is as sequences of assignment statements. You say, hey, R is something, and then S is something which involves maybe R, and then Q is something which involves maybe R, maybe S. Okay, so this is a sequence of assignment statements. That's the simplest sort of way of notation. Another way is as expressions with several operators, probably as simple as the previous one. So the way we constructed our expression was to have something inside and then apply on that, and then you get basically a big expression that expresses what you want to do. The last notation, which takes up more space but is actually equally expressive, is as an expression tree. Okay, so at a high level, what are the types of ways you can construct these more complex expressions? So let's see examples of this. Okay, so so this is an example of sequences of assignments. So if I had, for instance, a theta join with R3 is equal to R1 theta join R2 based on condition C, I can write that as 2 steps, with R4 being R1 cross product R2 and R3 being a sigma or a selection applied to R4. Okay, so that's a sequence of assignments. In this case, you can either explicitly use a renaming operation, or you can use renaming operation in a convenient manner, which is just to say R3 new attribute 1, new attribute 2, blah blah blah, is equal to R1, for instance. Okay, so the convenient way of doing a renaming as opposed to using a row operator, but they are essentially equivalent. So you can use either one. This is probably more convenient though. Okay, so this is a sequence of assignments. Now you could also build up expressions by using parentheses, and just like in arithmetic, just like in matrix operation, just like in any other algebra, there's a precedence order in which these operations are conducted. So the precedence is, if you didn't use parentheses, the precedence is fairly simple. It is, if you have any unary operators like select, sigma, pi, or rho, these are applied first. Okay, if you didn't have any parentheses, these should be applied first. So these are the unary operators. Then you have the products and the joins. Then you have the intersection operations and the rest of the set operations. Okay, so unary comes first, then comes join-based stuff, and then comes set-based stuff. Okay, so the set-based stuff have lowest priority compared to unary and join. If this is confusing to you, what you can simply do is to just use parentheses. If you use parentheses, you can force it to evaluate in the way that you want. Okay, so if you use parentheses and use parentheses generally or generously, you will be able to get the expression order you want. You don't need to worry about these this kind of precedence order rules. But if you didn't have parentheses, the precedence is as follows. You do the unaries first, then you do the products and the joins, and then you do the set operators. Okay? Questions? Right? So the last way of expressing these complex operations is as expression trees. The leaves in an expression tree are the relations, and you're constructing more complex expressions as you go up the tree. The interior nodes are essentially operators that operate on the relations or operate on the results of previous operators. So let's take an example to give you, let's start with the expression. I don't know if I'm starting with the expression or with the tree. Okay, so let's do the tree. So I'm trying to, I have these two relations, so bars and cells. Bars contains name and address. Cells contains bar, beer, and price. I want to find the names of all of the bars that are either on Maple Street or sell bud for less than $3. Okay? Does the question make sense? Okay. So let's start by figuring out how to do this. Any guesses on what I might start by doing? Okay, let me decompose this to make it simpler. Okay, so the first thing that I might want to do is let's figure out the bars that are on Maple Street part first. Okay, so I want to figure out the bars that are on Maple Street part first. I'll figure out the sells beer for less than $3 later. Okay, I'll figure that out later. So I want to figure out the names of all the bars that are on Maple Street. How would I do that? Okay, so selection on what? Okay, so you're saying start with bars and then maybe apply a selection with bars. Sorry, I didn't want to do bars. This is going to erase everything. Okay. Bars, sigma address equal to Maple Street. Okay, what next? For okay, so yes, but that's the other part of the query that I don't want to deal with yet. So let's focus on names of the bars. Actually, let me expand this out to be names of the bars that are either on Maple Street or names of the bars that sell bud for less than $3. So if I want to find the names of the bars that are on Maple Street, then what I've done is I've selected the bars that are on Maple Street, but I want only their names. I don't want anything more, right? So you project on the name, right? So you would do a projection, and then you would say just maybe name. Okay? So this part of my query is done. Now let's look at the other part. So the other part is I want to find the names of the bars that sell bud for less than $3. Correct? Okay. So which relation would that information be present in? Cells, right? Okay. And what would I want to do next? Selection on price, okay? But I want to make sure that they are selling bud for less than $3. So what would the selection condition be? Yep.
We have to put two conditions, beer is bud and
Okay, beer is Bud and price is less than 3. Okay? What next? Projection. Okay, so what would I want to select here? There is no name, right? In this case, it's bar, beer, and price. So what would I select? Huh? Bar, right? Okay. Okay, what next? What would the natural join give? Yep. Okay. So let's try a union and see what happens. So it seems like you should be able to do a union because these are two relations, both of which have just one attribute, and then you just want to collapse them down. However, remember that the union operation relies on the two relations having the same schema. Because the union operation relies on the two relations having the same schema, this is not going to fly. This won't work. So what I will have to do instead is, any guesses? Change the name. So rename, right? So I would have to rename one of them. Maybe I'll rename the bar thing by changing it to row, and the relation name really doesn't matter, and then name. Okay? So now I have two relations which both contain the attribute corresponding to name. So now I can do the union. Okay, so I do a union and I'm done. Okay, so this is how I construct the pieces of this query and then eventually construct a more complex expression from those pieces. Okay, this is how I would do it for a tree structure. Any questions about this? All right. If you are concerned about me raising that, the same thing is there here, so don't worry. All right. There are other ways of doing this, but actually, in the interest of time, I'm not going to go into that. So another way of doing this, and I want you guys to try this out at home. Try to construct the same query without treating these two parts separately. Try to start by doing a theta join between bars and cells. Okay, start with that as your first operator, and then do other things on top. All right. This is something for you to think about offline. Let's try a different type of query. All right, so this is a query where I'm trying to operate on just one relation. This is cells, which contains bar, beer, and price, and I want to find the bars that sell two different beers at the same price. All right? So how might I do this? So one thing, reading this question, one thing that should come to you almost immediately is that since I'm trying to associate multiple bits of information from the same relation, so I want to find two different beers that have the same price, I can't really do that by just working on that one relation, right? I can't just do union or rather unary operators like selection, projection, rename on just that one relation to get what I want. I have to associate the information in two different relations to get the information that I want. Okay, so the first instinct that you should have is I need two copies of cells at least to be able to do this query. Okay, and then I could take those two copies and do something with that to get what I want. Yes?
price quotients, price 1 and price 2, and then do some sort of join where price 1 equals price 2? I'm sorry, yeah, where price 1 equals price 2 and where the beer names are the same also?
Right, so in this case you want the beer names to be different but the price names to be same.
Right.
Okay, so that's a great instinct. So what you're saying is, I want, maybe you can take one of the cells relations, rename it such that I keep the information that I want to match across these two relations the same, and rename the other one, and maybe I can just do a natural join and then I'll be pretty close to what I want. Okay? Again, there are many different ways of doing this because essentially theta join is equivalent to a bunch of other operators, so you can re-express a theta join as other operators. Natural join, once again, is expressible as other operators. So there are many different ways of doing this. But the one that comes most naturally to me and is similar to what he said is the following. So the first thing that I'm going to do is I'm going to take cells and I'm going to rename the beer name. I'm not going to rename anything else. I'm just going to rename beer. Okay, so I'm going to start with cells, and then I'm going to do a row, and then I'm going to say rename cells such that you have bar, beer, 1, and price. Okay, so I remember that I need to associate two different beers at the same price. Okay, so in order to do that, I'm going to make sure that I have the beer information be renamed appropriately. Once I've done that, I'm going to do a natural join with cells. Okay? So what does this give me? What's an explanation of what this gives me? Firstly, what would this contain? What are the attributes that this contains? Bar, okay. Beer, okay, beer 1, and price. Right? So these are the attributes that this relation contains. And what is the explanation for what it contains? So what the natural join is essentially ensuring is that the tuples in this relation and the renamed cells relation have to match on the beer and on the bar and price, right? That's what is ensured by the natural join. So essentially, what this natural join gives me is the beer and beer 1 combinations where they are sold, both of them are sold at the same bar for the same price, right? So beer and beer 1 combinations where both of them are sold at the same bar and have the same price, correct? So yes. Exactly. Okay. So the next step is, is this enough? Maybe all that I need to do is I've already associated beers that are being sold at the same price at the same bar, right? So that's what this natural join gives me. Do I simply project everything else out and then have just the bars as part of the output? The answer is no, because so you're going to have, when you take these two relations, one cells and one renamed cells, every tuple is going to get matched with every other tuple that satisfies this condition, and therefore this will also ensure that the same beer will also get matched. So if you simply do a projection, that is not going to be correct. You have to do a selection. Okay, so let me work this out and then we'll see if this makes sense to you. So like she said, I'm going to do beer is not equal to, or not beer equal to beer 1. Okay, so I've basically ensured that these tuples are of two different beers that are sold at the same bar at the same price. Okay, this is exactly what I want. The last step is I want to select the bars. Right, so I would just project everything out except for bar. Okay, is it clear why we had to have this selection condition? It's not simply sufficient to have the pie. Yeah?
I have a question. So
Yes.
Like, let's say you have beer and beer one, but then you have them flip,
Okay.
right? So wouldn't it be like a duplicate tuple?
What do you mean by beer one
Like,
flipped?
projection
Yeah.
cancels out.
Yeah. Yeah. Any questions about this? Is this clear? Okay. All right. So think about how you would do this without using a natural join as a first step. Maybe using a cross product, maybe using a theta join, maybe using something else entirely. Okay, so think about all of these alternatives. Okay, so once again, I'm leaving something for you as an exercise here. I'm trying to find the phone numbers of all of the individuals who've made a sale, given these four relations: product, purchase, company, and person. I'm going to skip how you get to that and focus maybe on this. Let me see how many slides I have left. I want to make sure that I get to the end. Okay, so 6 slides left. Okay. Cool. So I want to find the phone numbers of people who bought gizmos from Fred. Gizmos is a type of product, let's say. I don't know if it's a type of product or if it is a product. Okay, let's say it's a type of product. It's a category of product. Okay, so here I want to find the phone numbers of people who bought gizmos from the salesperson named Fred. So gizmos is a type of category of product. Fred is the name of a salesperson. So this is essentially the way I can identify that information is that it's present in the purchase information relation. And then I want to find the phone numbers of those people, right? So I want to look at maybe the person relation which contains the phone number information. Okay. Okay, so basically what this is telling me so far is that I definitely need to look at product, I definitely need to look at purchase, and I definitely need to look at person in some way, because the information that I care about is in those relations. Do I need to look at country? No. As far as I can tell so far, there's no need for looking at, sorry, not country, company. There's no need for looking at the company company relation. Okay, so how would we do this? Yep.
Start by selecting all the products that are gizmos.
Sure. Start by selecting all the products that are gizmos. That makes sense. So let's start with that. Say product, and then sigma category equals gizmo. Okay. Good. What next? Yep.
You can select all the purchases that have Fred as a salesperson.
Okay, so say that again.
Select all the purchases that have Fred as a salesperson. Oh wait, that's a social security. Never mind.
Right. So okay. So let's try to do that. Right. So I want to find the purchases that are related to Fred. Correct. So if I want to find the purchases that are related to Fred, I need to associate the information in purchase and person, right? Because this purchase information only contains the SSN. The person information table contains the SSN and the name, correct? So maybe I might want to do, yeah?
If you just perform two select queries on person and find Fred's phone, Fred's SSN, and
How would you, if you just do a selection on purchase, how would you find on person? Okay, on Fred's SSN. Okay, okay,
get Fred's SSN,
okay,
and then you go to purchase and you find the buyer SSN
okay,
corresponding to the Fred's SSN,
okay,
and then you go back to person
okay.
to find the customers who want that.
Essentially, so that makes sense. There are many different ways of doing this, and that might be a perfectly valid way. I'm going to follow your suggestion because it seems like it will lead to a simpler eventual result. Okay, we'll see if it actually does. So the first thing that I've done is I've selected the gizmo, so I'm good with that. The second thing that I'm going to try to do is I'm going to find all of the purchases that involve Fred. Okay, so I'm going to start by taking, basically doing, it's essentially equivalent to what you're saying, but let's see if this makes sense. So I'm going to take person, and I am going to maybe do a theta join on SSN equals salesperson SSN with purchase. Okay, so what I've done so far is I've associated person and purchase based on the salesperson SN being equal to the SSN. Now I can select on the name of the person being Fred. Okay, so name Fred. Okay, so what I have so far are the purchases that are corresponding to Fred. Okay? The purchases corresponding to Fred. Now, what would be a next step? Yes?
So we're under the assumption that Fred is not a unique person, right? But rather we're looking at all salespersons named Fred.
Okay, so this is a bit of a, so the question is, are we looking for, so are we assuming that the name corresponding to the salesperson or the name corresponding to a person can't be, is it just the first name? Is it more complex than that? And if so, how would you actually match if it contained Fred, if it was not just Fred, but it was Fred Flintstone or whatever, then how would you do the match, right? So for the purpose of this example, think of the name containing just one name, so it's a first name. You can certainly construct a more complex example where you actually had to match the first name and the last name, and that was what was stored. This is a little bit of a toy example just to give you a sense for how these queries are constructed. Your point is valid because if I did want to match a partial part of an attribute, then the operators that I have with me are not sufficient. The conditions that I have with me are not sufficient, right? If the name was listed as first name and last name and I only wanted to find those where first name is something, then there's no way that my current operators can do that. SQL actually can do it, but relational algebra can't. So we are working within the constraints of relational algebra, trying to learn a little bit more about it before we get into some of the real issues that you talked about. Yes?
Then do you just, after this, do you data join with product and purchase?
Okay, so let's see what I do. Okay, so essentially I've done a join between person and purchase, so that's good. I found I have the information corresponding to all of the purchases where Fred was involved. Now I can for instance, do a natural join between both of these. So this natural join essentially associates okay, so okay, maybe before I do a natural join, I'll be a little bit more careful, okay, because I have the name appearing here as well, so I don't want everything to be matched. So, okay, gizmo. Okay, so to simplify matters even more, I'm not going to do a theta join. I'll do a natural join, but I will project out all the attributes that I don't care about to simplify things. Okay, so I have person and purchase. I'm going to use a pi operation, and the only attribute that I'm going to worry about is PID. Okay, so what this tree gives me are all of the purchases that involved Fred. Correct? Yes?
Sorry to come back to this, but isn't it if, I mean, a social security number is unique to a person, right?
Yep.
So how come are we also selecting Fred when we've already gotten a unique social security number, for instance?
So the salesperson's name is Fred, but the salesperson name is not stored in the purchase relation. The salesperson name is stored in the person relation. So the way to get to that information is to do a join between person and purchase, and then a natural join, theta join, one of those joins. In this case, it was a theta join, and then get to the Freds. Once you have the Freds, you have their SSN or their other information, right? So here, basically, what I've done, this subtree gives me all of the purchases that involve Fred. So that's great. That's an important step. Next is I want to maybe join these two. So this was the set of products that are gizmos. This is the set of, okay, actually, give me a second. I need to make sure that I'm not messing something up. So by SSN, so this is a product SSN. I can, so I have the purchase ID. Maybe I don't want to eliminate everything. Maybe I don't want to just keep the purchase ID. I want to also keep the buyer SSN. Okay, so yes, this is a complex example, and I'm struggling as I go along, but hopefully you will also figure out what it takes to build these things. Okay, so in this case, the reason why I added the buyer SSN along with the purchase ID is because I need the buyer SSN to find the phone numbers of the people who've done that purchase. If the only information I had was a purchase ID, the product ID, then I won't be able to find the information corresponding to the people who bought that product. Does that make sense? Okay, so far let me step back for a second and explain what I have so far. So far I have done a theta join between person and purchase. I found all of the purchases corresponding to Fred, or those that were sold by this person called Fred. So Fred is a salesperson. The two bits of information that I need from this is what are the products that Fred sold in that transaction, and who is the buyer SSN. So that's why I have gone and projected out everything else apart from product ID and buyer SSN. Are we good so far? Good so far? Okay. Next is I'm going to do a natural join between the products that are gizmos and the products, actually maybe, no, let me do this. So let's do a natural join between products that are gizmos and the result of what we had. What that gives me are all of the buyer SSN along with a bunch of other information corresponding to the buyer SSNs that bought gizmos. Yes?
Maybe you could have done a projection on product also so that you could just have the PIDs of the products. That would simplify the.
Yes. So your question, your observation was, I could have done a projection here before I did the natural join. You're absolutely right. So I'm going to do a projection here. I am going to retain. What do I want to retain? I don't want to retain anything apart from PID, right? So I just keep PID. And so I have PID coming from product. I have PID and buyer SSN coming from the other guy. And then the natural join is essentially going to have just PID and buyer SSN. Okay? Again, to simplify the result, I'm just going to project out the PID and leave with the buyer SSN. So these are the buyers who bought a gizmo from Fred. Okay? What's the last step? So how do we find their name or their phone numbers in this case? Yep.
Rename SSN in person to buyer SSN and then phone one.
Sure. Or I can more direct. So her observation was, I can take person, rename SSN in person SSN, rename SSN in person to be buyer SSN and do a natural join. Instead, another way of doing it is to simply do a theta join between this and a person on buyer SSN is equal to SSN, correct? And then finally, I'm just going to project the phone number. Okay? So this was not easy, but this is how multiple relation joins looks like. This is not entirely straightforward. So here notice that the person relation appeared twice because you needed to look up the phone numbers of people and also you needed to look up the names of the salespeople, right? Purchase showed up once because you wanted to look up the purchase that connected the salesperson Fred as well as the product IDs and the buyers, right? So these are all information that you needed from purchase. Product showed up because you needed to look up the products that are gizmos. Okay, so you can reason why each of these relations are present in this query. Any questions about this? Okay, so in 2 minutes, I'm going to show you. I don't remember the query that is in the next slide, so we'll see if it is the same or if it's different. Okay, so it's going to be a surprise. Or rather, how we wrote this out. So what I did, or past me, the way I did this was I essentially did the same thing, right? So I took product, I did category is equal to gizmo, and then I projected out the product ID. So I have this, and then I took person and purchase, like we did in the previous slide. I selected name is equal to Fred. I projected out their SSN information, and then I did a theta join, right? And then, so maybe in the previous case I did a sigma before or after the theta join, I'm not sure. But in this case, I decided to keep that information along and then did a product ID based join, which is the same as we had earlier, and finally looked up the person relation for the buyer phone number. Right? So roughly looks the same as what we came up with, but whether we did a natural join versus theta join, whether we did the selection first or did the selection later may be different. Okay, but otherwise the structure of the thing looks roughly similar to what I had in this slide. Any questions about this? Okay, all right. So I'll see you all on Monday.